The plugin, referred to as Synesthesia in Unreal Engine, provides a powerful set of audio analysis tools that enable lots of ways to drive events and parameters with audio. By analysing perceptual loudness rather than simple amplitude, scanning audio for onset events, and measuring frequencies using bands that relate to musical pitch, we can derive data that is meaningful and easier to interpret than some of the other analysis tools. In the Magic Forest area of the demonstration project, that's bookmark key 4, we can find an example of the kind of things that you can do with these tools. When the villagers of the demonstration project have had their fill of pumpkin cider at the tavern, they often walk to the forest to dance away the small hours under the light of the iridescent moon. They don't have a jukebox to play music, but they do have a set of enchanted mushrooms, which you can trigger using the key E. We'll come back and examine this system in detail, but let's start with something a bit simpler. We're going to set up a simple blueprint that will enable us to take a look at the 3 synesthesia analysis tools in turn. First, we'll create a new blueprint of actor class, and we'll call it demo mushroom. We'll open that up, and what we're going to do is add a static mesh component to this. And we'll find one of those mushrooms to use. And we'll also add an audio component. And we're going to use the audio to manipulate that mushroom. And I know that the sound I want is called bass, demo mushroom bass. And I need to set this to not auto activate so it doesn't start playing straight away. What we're going to do instead is loop it within the blueprint. So the first thing we want to do is to bind to this an event, and it is event on audio playback %. I'm going to put a little delay in here because we just need to make sure that everything in the level has loaded successfully before we bind our events. So that's going to give us a custom event. And from that, we get the name of the playing sound wave and the playback %. That is the percentage through that sound wave that we're currently at. Now, in our case, the name of the playing sound wave isn't going to change, but if you're using a sound cue with randomized elements, then this is useful to know. We need a synesthesia analysis asset for each individual sound wave. So later in the mushroom music blueprint, we'll be using this to help us pick the correct synesthesia asset for the particular sound wave that's playing. Next, we're going to set up a timer by function name, and the function name we will choose will be play, and that will loop around and play our audio component. So we'll play it here, and every time it comes round, it's going to use this custom event called play. So effectively looping that sound. Now let's go and have a look at our sound. We'll find it in the content browser. And we can see that it's 6.233 seconds long. Now this sound itself is a perfect loop, so I can go straight from the end back to the beginning and it loops perfectly. It doesn't have a decay tail we need to account for. So I can set this time 6.233. And now let's just create a print string so that we can see what's coming out of this playback % output here. We'll just drag our actor into the level and play. So you can see that playback % on the left. Now it restarts, so we're getting values between 0 and 1 every time that timer comes around. So now in our content browser, we'll create a new analysis synesthesia asset, and it's going to be a analysis type loudness, so we'll call it bass loudness. And if we open that up, you see we need to tell it which sound to analyze. Now we know that's called demo bass or demo mushroom bass. It's got a default settings asset referred to here, but let's create our own. So sounds, analysis, synesthesia, NRT, settings this time. NRT just stands for non-real time. So we'll call this bass settings and we'll assign that here. We'll take a quick look at this. Now our bass probably doesn't go up to 20k, so I think we can bring that down a bit. We'll just leave the other settings at their defaults. The analysis is performed when the object is made or whenever a property of the settings is updated. The good thing about the synesthesia analysis is that it takes into account human perception. Our perception of loudness is partly dependent on the frequencies within a sound. And so this doesn't just give us the straight loudness in decibels. Instead, we get values that represent how loud a sound might actually be perceived to be. So now we've got those synesthesia assets, we need to create a variable to reference them here. We'll call this base data, and we'll make the variable of type synesthesia loudness NRT, and when we compile that, we can find our base data to reference. Bringing that into the event graph, we're going to get loudness at time, and the other thing we're going to get is its duration in seconds. So we've got playback percent here, which gives us values between 0 and 1, and we've got the total duration in seconds of the sound file. So if we multiply these two values, what we're going to get is the current playback time, which we can feed into the get loudness at time node. So now let's have a look at those loudness values. Okay, so we're getting loudness values in dB with highs of around -20 and lows of around -50. We're going to use these to adjust the scale of the mushroom so that its height reflects the loudness of the bass part. So we'll get a reference to our mushroom and we'll do set relative scale. We'll split this struct so we can see the individual x, y, z values. We'll keep x and y at 1 so that they remain unchanged. And z we want to add to it, so we'll create a float plus float that's going to add something to the value 1. And then we need to map these loudness ranges to something appropriate. Now we'll use the map range clamped and we'll map the ranges so that -50 becomes 0 and -20 becomes 1. And we'll add that onto 1 so that we're increasing the scale of that mushroom. So now we can see the height of that mushroom responding to the perceived loudness of that bass sound. Just take out that print string and just tidy this up a little bit. Now, one thing worth remembering is that you don't need to play the same sound file that the synesthesia analysis relates to. In other words, you could have lots of synesthesia assets that contain the analysis for all your stems or musical elements, but if the piece of music that these elements create is actually fixed or unchanging, then you could just play back a stereo mixdown of that and just use the two voices, while using this sound to drive the playback percent and read through all of the analysis data. You don't actually need to play back all of the sounds that are being analysed and use all of those audio channels. We'll see an example of this later in the mushroom music blueprint. So loudness is good at tracking continuous changes in a sound, or for triggering things when the loudness is over a given threshold, which you do with a branch. So let's just have a quick go at that. We'll create a branch node here. And what we'll do is we'll get this value and we'll say, well, if that is bigger than, let's say 1.75, then we're going to do something else. And the something else is going to be a particle system that will activate. So we'll create a particle system component and we'll find a little particle system to turn on. So I'll look for PAU taunt sparks, which I found earlier. And that's from the Infinity Blade assets. So when the loudness goes over that threshold, what we'll do is we'll activate that particle system like this. And actually we'll add a little do once system here to stop multiple triggers. And then we'll delay by 0.4 and then open that back up again. So you can see that particle system firing off only when the loudness goes across that 1.75 threshold. Next, we'll look at the constant Q analysis. This is really useful for analysing monophonic musical sources since it creates analysis frequency bands that align to musical pitch. So back in our blueprint, we will add another audio component, and this time it's going to play a flute part, which is just a simple ascending scale. And we'll remember again to set that not to auto-activate, because we're going to play it back just like this one using that timer. So in our content browser again, we're going to set up an analysis. Here it's going to be constant Q NRT, and we'll call that flute data. And we'll assign that flute part that we just added, demo flute gap. Now again, this has got some default settings, but we'll create our own. So analysis, synesthesia, NRT settings, constant Q, and we'll call that flute pitch settings and assign that here. Now this particular flute part is simply a C major scale, so it starts on the C above middle C or C5 and it goes up to C6. After looking up the frequency of the note C5 in my very useful encyclopedia, I know that this note occurs at a frequency of 523.25 Hz. So back in my analysis settings, I can make the starting frequency of this 523 Hz. Now we've got 12 bands per octave, which align to pitches, and we're going from C up to C, so we actually need 13 bands or 13 notes, the 13th note being that top C. We now need to create a new variable which we'll call flute data, and this is going to be of type constant Q. We'll compile that and we can get our flute data here. Add that to the event graph, and we're going to get channel constant Q at time. And for the time we can use this same variable from here. So every tick, what we're going to get from here is an array containing 13 magnitude values, and those are aligned to our 13 musical notes. What we're interested in is to find out which note is playing. So if we get max float of array, what this is usefully going to tell us is the index of the loudest note in that array. So let's create a print string and we'll run it off a sequence here. And we'll look at what index we're getting. Okay, so we went from 0 up to 12 there, and that's of course because you remember that arrays start at an index of 0. So we're getting notes 1 to 13, but they are within array indexes going from 0 to 12. So bearing in mind the tones and semitones in our musical pitch, you can see that the indexes aligning to these notes should give us 0, 2, 4, 5, 7, 9, 11 and 12. Now we're getting lots of instances of those, so what we'll do is we'll get the max value and we'll compare that to a float value, let's say minus 35, which we'll treat as our noise floor. So it's only when a note is above that value that we will actually do something. So what shall we do? We'll use the index to control the height of some actors that will spawn into the world. So we'll spawn actor from class, and we'll use a blueprint class that we've made. It's called mushroom spawn. It's very simply got a mushroom static mesh within it. So when there's a note, we'll spawn that. We'll split this open so that we can control where we spawn it. Now we'll keep the Y location static at 40, 50, and we'll multiply the index by a float, let's say 40, so that we get some height differences, and we'll add that to a basic starting position of 2400. So our height should reflect the index that we're in, and in this case we're just playing back an ascending scale, so we should get an ascending height of these mushrooms. Now we don't want them just in a vertical line, so we're going to need to do something with this x-axis as well. We'll add again to a fixed starting point of minus 340, and this time we can use the playtime in seconds to take us across that x-axis. So we're going to need to multiply that by something. So we'll get it here, and we'll multiply it by 150. And then add that to the starting position. Okay, so the second time round it was just spawning those on top of the previous one, so we're going to need to add a bit of a cleanup system here. So every time we start playing, let's get all actors of class, and it's that spawned mushroom class we want to find. And for each of them, we want to tragically destroy them because they've served their purpose. It's harsh but fair. Now you'll notice a couple of things about that. Firstly, this spawn is being triggered multiple times by this playback percent event when the branch opens. And secondly, there's a few odd pitch anomalies when we're in between or changing notes. These will be more evident if you're using material that's played in a smoother or more legato manner. Now we could add a do once and a delay to stop the multiple spawning, but we might miss some important changes during that delay. What we need is something that tracks the onset of audio events. Unfortunately, that's just what we've got with the Synesthesia onset detection mode. So now we'll create a synesthesia analysis asset of type onset. And we'll call it flute onset. And again, we'll create some onset settings. Call that flute onset settings. And assign it here. And again, we're going to look at that flute gap 1 sound. So now we need a new variable, and that's going to refer to our flute onset asset, so we need a type of onset NRT. Here, compile, and find our flute onset asset. And with this one, we're going to get normalized channel onsets between times. And the times we're interested in is the start of the sound and the end of the sound, which you might remember is 6.233. From here, we're going to get a set of timestamps of when those onsets start and the strength of those onsets. So let's take a quick look at what we're getting out. So we'll create a for each loop, and that will go to a print string. And we'll see how many onsets we're getting. And we'll just feed that from another bit of the sequence here. Not very efficient, but it's just for demonstration purposes. Actually, let's put a do once in here so that we're only seeing the onsets within that time frame here rather than this being re-triggered multiple times. So we'll grab that and do that. Okay, so how many onsets are we detecting within that flute part? Quite a few. So this is when we go to our onset settings and we play around with them. So we'll make it quite a lot less sensitive. And we know it only starts at 500 Hertz, our flute part, so we can change that as well. And I'm just going to change the granularity in seconds because I know already, of course, that this gives us the results we want. So there we've got 8 onsets for our 8 notes. So instead of just spawning loads of actors every tick, should this be true, we're going to actually check through this now and only spawn the actors when the time is approximately near to one of those onsets. So we're going to use a nearly equal node. And look at each of those onsets and compare it to our current playback time. And if that is indeed nearly equal, that is when we will spawn our actor. I just need to tweak this error tolerance a little. So now hopefully you've got some idea of what we can do with these synesthesia analysis tools. We can get loudness at a particular time, and that's perceptual loudness. We can get channel constant Q, and that often relates to pitches. And we can get normalized channel onsets, and that's using onset detection so that we can accurately tell when particular sounds are starting. And often there's situations where you actually want several of these things operating in conjunction with each other. In the next video, we'll be seeing how these same tools have been implemented in that mushroom music blueprint.